Now the content of my presentation is, first I will discuss the origin of the Wacker's oxidation. Second one is the mechanism of the Wacker's oxidation through the catalytic cycle, then some useful extensions of the Wacker's process, then I will go through some chemoselectivity of Wacker's process, and then summary, and then I will tell about the references that I have used for this presentation. Now in this slide I am going to discuss the origin of the Wacker's oxidation. In 1894, the MSc Phillips reported that the formation of acetaldehyde and the precipitation of metallic platinum by passing the ethylene into the aqueous solution of PdCl2. So here is the reaction that the platinum 2 plus is going to platinum 0 with the formation of the acetaldehyde. And at that time the platinum 2 plus was used as its qualitative analysis. But after the 1859, when the Smith and Wackers reported that the reduced platinum 0 is reoxidized to platinum 2 plus by the base metal, that is CuCl2, and which is reduced to CuCl, and the CuCl is easily reoxidized to CuCl2 by using oxidation. Here written is platinum 0 is going to platinum 2 plus again, and the Cu2 plus is going to Cu plus. But what was seen is there was a very small equilibrium constant calculated for the oxidation of platinum 0 and Cu2 plus salt, and the reason for this was the platinum is a noble type metal that is not oxidized easily, and the copper is a base metal that is easily oxidized. So the solution for this problem was the oxidation is finally carried out into the aqueous HCl. What happens is, in the presence of aqueous HCl, the Cl minus ion stabilizes the platinum 2 plus and the copper plus by the complex formation. So here we have seen that the CuCl in the presence of oxygen reaction is going with Cl minus also, and the formation of again CuCl2 and the water. Now this is the overall reaction, and the net reaction is the oxidation of ethylene with oxygen and the formation of the acetaldehyde. This is the whole process, and this process is known as the Wacker's oxidation, and this is the first example of the oxidation of organic compound with the platinum 2 in the heterogeneous phase. Earlier in the earlier period, before the report of this reaction, generally the platinum 2 was used in the heterogeneous phase. And the last point of this slide is the platinum modifies the chemical behavior of ethylene to enable the reaction to occur that would not be possible in free ethylene. I will discuss this point in the next lecture. Here is the catalytic cycle of the previous catalytic reaction what we have seen in the chemical reaction. Here we will start from here and complete to this process. First step is the reaction of ethylene with the platinum 2 plus complex. Actually, generally the ethylene do not react with any nucleophile in this phase. Generally, when the ethylene go in reaction, it has an electron withdrawing group with it, so that the electron density of this pi orbital decreases and the nucleophile get a chance to react. Similar thing is happening here is the metal is coordinated with this ethylene in this process. Metal is coordinated with this ethylene, and the pi electron density of this ethylene decreases, and that is why the water is acting as a nucleophile here. So water with its lone pair attack on this alkene, and this pi bond break on this metal, and there is a formation of this complex. Here, after the addition of water, the one proton from the water is removed, and since here in the first step there was a removal of Cl minus, so there is a negative charge here, and again there is a H positive removal, so there will be a total charge of 2 minus here. Now what happens is, here we have CH2. CH2 and this H is a beta H. This H is a beta H, and the CH bond, I can show it like this. This CH bond. So this electron pair of this bond is shifted to the platinum metal, and the electron density of this platinum CH2 bonds is shifted toward this one, and this is called the beta elimination process. And so the finally what we have seen is the Cl minus is removed, and the H at the beta position goes to the platinum. Now again the Cl minus undergo reaction. What happens is this H is going to shift at this CH2 position, and again this pi bond is going to shift at this platinum position, and here this process is called the migratory insertion reaction by the hydrogen atom. And now again this moiety is going to attach to this platinum complex by the sigma bond, right? Now what happens is again the beta elimination occurs. How it occurs is this carbon is a alpha carbon, and this oxygen is a beta oxygen with respect to the position of platinum. That's why this hydrogen is also a beta hydrogen. What happens is this OH bond gets shifted to this position, and this bond gets shifted toward the metal, and the Cl leaves this group. And what we get finally is a acetaldehyde is formation, because here will be a double bond formation, and this H is shifted to this position, and here is the formation of acetaldehyde, which is coordinated to that of platinum. So finally, by the reductive elimination, the product we get is the acetaldehyde with HCl and Cl2 minus, and the platinum 2 plus is changed to platinum 0. Now what happens is the platinum 0 is changed to platinum 2 plus by the use of Cu2 plus. Actually what happens is Cu2 plus changed to Cu plus, and again the Cu plus in the presence of O2 and that of HCl, it again goes to copper 2 plus, and completes the whole cycle. And this is the way by which the Wacker's process works. Now these are the steps that I have written. Finally, that I have told is the written in the slides. And now it has been established that there is no incorporation of deuterium occurs by the reaction carried out in D2O, and the 4 hydrogen in ethylene is retained in the acetaldehydes. This indicates that there is a hydrogen shift occur in the Wacker's process, and that I have shown here is there is no change in the product here. Now in the next step is, if the solvent is used is not water, it is other than water, like the oxygen based, alcohol or acid or N based nucleophile, then the product changes. The final step doesn't occur in that process, and the complex dissociate to give a vinyl product. For example, for the oxidation of ethylene in alcohol with PdCl2 in the presence of base gives the acetal of acetaldehyde and vinyl ether. Here is the acetaldehyde, this is the major product here, and the vinyl ether is a minor product here. So, and similarly the oxidation of ethylene can be in acid also, in amine also, and the product will vary according to the using nucleophile. Now here is some useful extension of the Wacker's process. First one is the conversion of terminal alkene into the methyl ketone. This is the very useful part of the Wacker's process, and in this process generally the terminal alkenes used is of higher order, that means a longer alkene is used, and for that we generally use the DMF as a solvent, and the platinum 2 collides as a catalyst, and the copper 2 plus or the copper plus collide, and the 1 atmosphere of oxygen. Generally in this reaction what happens is, in the place of CuCl2 we use CuCl in the preference. This is because this avoids the formation of alpha chlorinated alpha chlorinated ketones as a byproduct. That is why we prefer the copper plus collide. And again, the second extension also is the preparation of 1,4-carbonyl compound. Here is the conversion of 2 allyl ketones to the 1,4-diketones. Now here I have shown the chemoselectivity of Wacker's process, that is the external and internal alkenes, and generally the reaction occur on the terminal alkenes, and the internal alkenes is very less reactive as compared to that of the terminal alkenes, and what we are seeing here is the 90% product, and the terminal oxidation occurs. Similarly here also the internal alkenes of the ring is not participating in the reaction, and the terminal alkenes is participating, and so this is the change in the reactivity in the comparison with the external and internal alkenes. Now the steric hindrance also works. Here it says both are the terminal alkenes, but this alkene is getting reacted in after 3 hours of this reaction. What we are seeing is this terminal alkene is getting oxidized, and finally this one also, but this takes too much time, so it's very more reactive. And again the similar example is written there. Now the summary of this Wacker's process is, this is the oxidation process of alkene, no doubt, and the success of this process relies in its ingenious catalytic cycle, right? And the Wacker's process has found its most use in the oxidation of terminal alkenes to the metallic ketones in industry. So at the industrial level this one is very useful. And the fourth point is, the reaction has advantage of selective oxidation of the terminal ketones in the presence of the di or tri-substituted alkenes, and besides these alkenes many functional groups are also inert toward this process. And the last one is, the instead of water using alcohol or acid or amine give extension toward the industrial path also. Here is the references. First one I have used is the transitional metal reagent and catalyst by the Zero Suzy, and second one is the modern method of organic synthesis, that is of William Carothers and the Colham, and the third one is the organometallics and bioinorganic chemistry by the Ajay Kumar, and last one is the Carothene E. Haustcraft, that is also an inorganic book. So thank you so much.